What am I supposed to do? No, full screen.
Double click.
Hmm?
Oh, no, it's fine. You can double click on the middle of this image.
Oh, I didn't know that. Double click on any window.
No. It gives the full screen without the task.
Yeah. Oh, otherwise the taskbar
And the top.
is save a bit of space. Let's three, seven.
Can you click OK?
Still?
No, OK.
Oh, this meeting is being recorded.
Just go.
Okay. Well. Some more. Few more minutes. Now it's clean, right? Ah, yes. So homework 7 officially was due in the past. Write it. You guys take extra time. Say that again. Do you have concerns about homework 7? No, you guys keep smiling at each other.
Actually, it was quite interesting. I thought animation.
Is that the joke about?
For the time.
About the time?
For the time. Yeah.
Which time?
I mean, the time it's going to take.
Oh, it's going to take. But all the steps are in there, right?
Yeah.
Has anyone finished? I think Ryan, you have finished, I know, huh? You have finished. Manuka, you have finished? Oh, no. Has anyone finished? Almost 7 other than Ryan? Okay. Has anyone started? Homework?
Yeah, we
Okay. This is you. Cute. And midterm 2 is in a week. And it will be like last time, I think. Yes. Those- those- those are the things. Next section. Yeah, I have started thinking on what problems to give, but not yet made any clear, but I might be able to give more ideas on this step, but in general, whatever you have learned between the two, or in general, everything, it is not necessary. It is comprehensive in the sense I can ask anything from the first part of the semester, or like first day of the lecture to today. Having said that, content between midterm 2 and midterm 3 is what I will concentrate on. But officially, it is cumulative. I can, like, for example, functional derivative is there all through, right? That's what we did most of. So be prepared, and by now you have got used to functional derivative. Hopefully, you've got used to functional derivative sufficiently. But I will be concentrating on, so there will be a problem of Lagrange multipliers, or I intend to put a problem on Lagrange multipliers, Lagrangian, one Lagrange multiplier, and now we are doing variations problem, so I'll come up with few. I have few things in mind, but let me think more on. So that's about midterm. Anything else you want to point out? Yes.
How many division?
Surely five. I think last time it was, how many? Five, right? Four or five, yeah, usually I aim for five, and if it is by any chance, I feel that it is a little lengthier or trickier, then I might make it four just to save you on time, but then that is more expensive on you in the sense if you get it wrong, then you lose 20 points immediately. So that's the issue with making it four problems. So yeah, if I feel the problems are shorter, then I might even include six. It seems to me that these problems might be a little longer from when I'm trying to think from my perspective, how you guys will feel, which is often wrong. It's not easy for me to have a perspective from your point of view. So we'll see. So that's what it is. Does that help? So, but it will be exactly like the midterm one, and I realized midterm one, at least you guys pointed out that it was a little harder. So aim for that. So not, I won't make it harder, but let's have that as a reference, and then we will go.
Okay.
Okay, we started doing stationary action principle by including the variations at the boundary, and we began the derivations. Stationary. So. No, good. Variations at boundary. Remember, earlier we were saying that it is a zero at the boundaries. That's what we want to do. Or in fact, we want to make variation in everything, like whatever the action depends on. Earlier, we were not talking about T1 and T2, the time quantities. We are now varying everything, and we want to see what all we can learn from that. So the action is, it's good to work in both formalisms. Last time I did a review of Lagrangian and Hamiltonian with the variations kept zero. Here I will do it for the Hamiltonian formalism. You should be able to do this for the Lagrangians. So the expectation is that you should be able to do this for Lagrangian. It goes very similarly, if you remember yesterday, whatever we did, it's very similar. Yeah, that's. Or change of plans, I'll do it for Lagrangian and you guys do it for the Hamiltonian. Okay, either way, so I think sometimes Hamiltonian is easier because it's linear, and Lagrangian has this time derivative in it. So let me do the Lagrangian. It might be a little, maybe a little hard. So there is only the difference in the Lagrangian and Hamiltonian is that Lagrangian has only one variable. The position is the variable, if you want, functional, and you say it is a functional of something. So this is what you vary. So there is only one variable, generalized quantity you have, but or dynamical variable. If you have in Hamiltonian, you have R and P. It also depends on time. And time, since it's evaluated at from integral, it's an initial point to the final point. If you want, you can kill T1, set T1 equal to 0, and then you will see it as a function of time. But let's keep both, it's not very hard to keep it. So that's equal to T1 to T2 to T. And Lagrangian is all as a function of time. Usually, whenever you have implicit dependence, you don't write it. You don't write the explicit dependence like that. But here, just in this expression, I'm going to write that. So this is d by dt of r. Then that is time. We will start varying with time, and we should know where are the implicit and explicit dependencies in time. So it's good to notice there are how many 4 places where time shows up, right? It is like saying if I were to take a partial derivative of this quantity, then which are the times it will hit on? If it is a partial derivative, it will hit on explicit times, and explicit times are these. So these two are explicit. And these two here are implicit.
Partials will only.
Partial act only on explicit, very good, so let me point that out. Partial derivatives act only on explicit. So this is the understanding here, and this is how you, when you're manually working, you need to know where to do the differentiation, right? So partial derivative acts only on explicit variables. And total derivative, d by dt, acts on both implicit and explicit. That's one conceptual difference, but when we are doing it, that plays an important role. And remember, our stationary action principle is that you make a change in the action. It's like calculus, find the difference, and then you want to see what are the changes that is happening. So here, currently on the left hand side, there is r that can change. That's a whole function itself that can change. And it can also change T1 and T2 that is at the boundary. You're not really changing time in the sense of this is where the time shows up, right? The whole, if you want to think of this as a function, so this is where the whole function shows up, right? So this is r as a function of time, let's say 1 dimension. So this is r as a function of time. And that's your t. That's T1 and that's T2. Right, and when we say that we are changing time, what we are saying is that T2 can go from here to T2 plus delta T. Okay, if it is 1 dimension, I can only go this way or that way, and how much I go is completely arbitrary. I don't decide on that. So that's the variation here talking about, and how that changes the action. So we want to calculate r plus delta r and T1 plus delta T1 and T2 plus delta T2, right? And then subtract out the original piece out of it. It's space. And this is clear how this goes in wherever you see, or replace it with the arbitrary variation in it. So this is T1 plus delta T1, T2 plus delta T2, dt, notice time doesn't change at all. Time is a dummy variable. We are not changing it. It's only on the boundary that shows up because the action is what we are changing, not the integral. This is R, and now I'll stop writing the implicit dependencies. That's delta R. Remember, delta R is implicitly dependent on time. That's an arbitrary variation in the function. So that's R and d by dt. So this is dr by dt plus d by dt of delta R. And you have t. This we have been often saying V, this we often say is V, right? That's your V if you want. It's just a shorthand for that, and this is the variation in the V. And what comes out useful is f of x plus a is equal, or f of x plus a minus of f of x is equal to a times derivative, partial or total. In this case, there is only one variable, so partial and total is the same, and there are higher orders. So if a is small, that's the leading order in a, and rest everything are higher orders. That's your construction. And if we are doing change in the action, you have to subtract these quantities. This from your original piece. If I want to subtract the original piece, so the original piece will be going from T1 to T2. So it will help a lot if I can change this by substitution, make some substitution, which I'm allowed to in an integral, so that you can change the limits going from T1 to T2. And what we do in a usual integration problem, we know that whenever we make a substitution, the boundaries change. So the substitution we will make here is t, so we are going to making a substitution, t in the dummy variable. So t prime is equal to t minus delta t as a function of time. Like, remember, if you're doing sine theta, right? If you're working on an integral like dx, 1 over x squared plus a squared, then you will substitute x is equal to a tangent theta probably, right? So that's a new function you have substituted, right? So this is a function, but that whole function I have written it in this form. So delta t, it's a small function, but nevertheless an arbitrary function. It could be any function that you can think of. Only one condition I make on this condition, because this for my utility, I'm doing this for a purpose, is that I want to get rid of this delta t's on the boundary. So I will set it in such a way, I'll choose it in such a way that when t is equal to, so this is t, right? This is t, that's t, right? When t is equal to this, when t is equal to that. So let me say what happens when t is equal to t1 plus delta t1. So that then your new variable, substituted variable, is t1 plus delta t1 minus of delta t of t1 plus delta t1. Right? That's how it works. That's equal to t1 plus delta t1. This is already a small variation. A small variation in a small variation will be a higher order term. So I don't have to worry about this delta t in this case. So this is equal to delta t evaluated at t1. So I'm introducing a substitution and I have a choice in selecting this, right? So I'm making the substitution. So I have a choice in selecting this. So I will select this to exactly cancel delta t1. Right? The variation that I'm making, the substitution, the variation is still arbitrary. Remember, this is arbitrary variation. The only thing I'm doing is that in my new substitution that I have, I'll choose this at t1 to cancel away that, so that I can I can get back my original limits. So this is a condition I'm putting. Should be equal to delta T1. If that is the case, these two cancel out and I exactly have T1. So if I make this substitution, my lower limit becomes T1 in the T prime language. So same thing, T is equal to T2 plus delta T2. And T prime is equal to T2 plus delta. And again, have delta T evaluated at T2 is equal to delta T2. That's and that's again the same, so that's equal to T2. Is that clear? Okay, that's it. So I'm making a substitution in this integral, and I've started with the limits. When you make a substitution in the integral, you have to change the limits. You have to change dt, right? If you're doing from minus infinity to plus infinity here, right? Let's say this is x equal to minus infinity, x equal to plus infinity. I'll first do the limits when x is equal to minus infinity. This is pi minus pi over 2. That's plus pi over 2. Right? These are the ways you go, right? And then I will say change dx. So you will say that, oh, dx is equal to a secant square theta d theta. So I have to say this is a secant square theta d theta. So I have to find a relation between dx and d theta between the variables. So I have to do this. And then finally substitute wherever I see a t, I have to change that to the new variable. So this will be a square tangent square theta plus a square. Just giving you an analogy of what is happened. So what are the things you have to do? First work on the limits, or let me do it here. First work on the limits, then the differential element, and then the substitution finally. So there are 3 steps here to make. So I've worried about the limits now. Now let's talk about dt. How does dt change? Right? So maybe I can use the space here. Oh, let's do that. Okay. We have t prime is equal to t minus delta t times delta t as a function of time. I'm interested in dt in terms of dt prime, right? Dx in terms of theta. It's the same idea here. So just do dt prime. That's equal to dt minus here this will be dt times d by dt of delta t. So you can say this is the same as dt times 1 minus d by t delta t, which is a function of time. I'm going to let me write it once more. This is not very useful because this helps me replace dt prime. I am interested in replacing dt in terms of dt prime. That means to say, if I get dx as a function of d theta, that helps. But if I have d theta, that doesn't help very much. So I had a, one would think that I can put this in the denominator. No, right? So if you put this in the denominator, then you have to replace theta with respect to x. So there's more work. So instead, I go back and go back from the first step. So that's t is equal to t prime plus delta t. That's a true statement. It is equivalent to saying that if you have a function x here, then I can solve for theta and start working with angle theta. But now this is a function of t, right? Not t prime. Substitute this again. T prime plus t is t prime plus delta t again. As, and you can keep going further and further. But I am doing infinitesimal quantities, so in the leading order, I will have only the first order coming in, so this is t prime plus delta t as a function of t prime. That's so only because we are doing infinitesimal quantities is possible to invert it very easily. If that's my function, this is the inverse function in a sense. Do the dt again, so dt is equal to dt prime plus dt prime. There's only one variable, so no worry about partial or total. That's the same as dt prime 1 plus. So I need this to substitute here, right? So that will give me a dt prime immediately. So that's the idea. But now we have one more place where the time shows up, and that's the derivative, right? We know how to substitute t. We will simply write t prime is equal to so on. But what about derivative, right? So we have to be able to substitute derivative also. So let's see that. So d by dt acting on a function is equal to, I want to write it in terms of t prime. So the way to do this is dt prime over dt times d by dt prime. Right? So that's a chain rule you will employ. And this we already know, right? Dt prime over dt is this quantity here. So this is equal to 1 minus d by dt of delta t. And these time derivatives are acting only on this. It doesn't act on everything on the right. So be careful about that. So that's dt prime. So we have that also. Clear? So now we have everything that we need to replace all the t's with t prime. So let me copy these things somewhere here so that I have space. Unless I do that, but camera doesn't go that way. One dt and t. And next. Okay, so we go back here, the change will be, so let me directly write change in the action. Change in the action will be this minus the original, right? That's my change in the action, this quantity minus the original quantity. So this is equal to, I changed my limits t1 to t1 plus delta, t1 becomes t1 to t2. dt here, using the language, using the substitution, I have dt prime 1 plus d by dt prime. And the Lagrangian itself is L of R plus delta R. I have d by dt's here, so I'm going to write that as 1 minus d by dt prime. Oh, this was d by dt, substituted again, right? So this was d by dt, right? Check your notes, I did copy this correct, so, but we know this again, right? So this is one minus d by dt again becomes d by dt prime over dt and d by dt prime delta t times d by dt. Substitute this again, dt prime over dt is one minus that, but this is second order, so to the leading order, this is the same.
We're doing two substitutions.
Correct. So I had d by dt here, but d by dt is again use chain rule, right, or recurrent statement. I put this inside itself. So this becomes d by dt, but now I have to expand this out. When I expand this out, I get another delta t, but I keep only the leading order. So in the leading order, that's just the first term that contribute, which is exactly this. Is that clear? Did I confuse? Maybe this one here. So this is equal to one minus dt prime over dt, go there. One minus d by dt times delta t. Right, I'm substituting this also in here. Okay, and d by dt prime times delta t times d by dt prime. Okay. Seems like it has got very complicated, but this is higher order, right? So this is one minus one times this, that's d by dt prime delta t. And this is having two delta t's in it, so it is plus order delta t square, which we are not keeping, right? This is an infinitesimal calculation. I'm keeping only to the leading order. So if I have the leading order already, then I can neglect that. If it was not a leading order calculation, then I worry about it. So this is a second order, so one times this and this times this is a higher order. And so this is the same as this one here. I brought this. So that's what I want to use here. So this is d by dt prime. So because everything is, I want it in terms of dt prime. And this is d by dt prime of r plus delta r. Is that clear? So remember again, this whole thing is coming from d by dt of r plus delta r. This d by dt is this whole piece. So instead of one variation, I have four pieces there. Out of which one will be, there will be three in a sense because two of them will be higher order. And dt, t, here there is t, where t is t prime plus delta t. With me? Not satisfactory? Is that clear why there are these terms? Yes, I just substituted that, that's its order. It should be clear, hopefully it's not confusing. Since it is delta change, I will also do T1 to T2 dt. Now I can write dt prime L, right? So the whole Lagrangian to begin with, whatever that was without the variation. Okay. Let me rewrite this, clean this up a little. That looks visually it is better. And I think this bracket was not needed, I suppose. L R plus delta R. Now, let me see this, there is a one acting on dr by dt here, so that's velocity, so maybe I can do that here, so that's one minus d by dt prime of delta t times dr by dt prime plus d by dt prime of delta r. That's my second variable inside of the Lagrangian. Expand this out. That's velocity if you want, v, with that t prime dependence. And this is plus d by dt prime of delta r, right? One is applying on this. And finally, we have this here, which is plus v times d by dt prime of delta t. Prime. There is one more term here, delta t and delta r, they are higher orders. Whenever I get two small quantities, they become higher orders. I don't keep that. So I have only three terms instead of four. So let me keep this here. So that's v plus d by d prime delta r and plus v times and finally,
Is it plus or minus?
oh, should be minus, yeah. One times this, good,
Second time.
plus, and the third one will be minus, very good, thank you. Very good catch. I would have struggled later on. Because these were in the words, later on. Okay, thank you. All right. Anything else you can see? Missing? Good. And finally, this is just Lagrangian. Let me be more explicit. Here, dt prime, this is L R V and T prime. Expand it out. We'll to expand Lagrangian. This is T1 to T2 dt prime. Keep this expanding this function. Remember f of x, y, x plus a, y plus b. And this time I have a z, or it's actually not even y plus b. This is of the form y plus b1 plus b2, right? And z plus c, like this is a function of that kind. Then what you will do is this is equal to f of x, y, z plus a times derivative, a partial derivative with respect to x plus b1 plus b2 times partial derivative of f with respect to y plus c times partial derivative of f with respect to z. And I had asked you guys to show this in the quiz, right? But Doesn't seem so. Yeah, good. So this you guys did as part of quiz, in a sense, right? So we are just going to use that. So first piece is just f itself, right? Or the Lagrangian itself. So if you allow me, I'm just going to write L without the variables in it. So next term is plus delta R dotted with partial derivative of L with respect to R. Right, it's a vector, so it's a gradient of L. The next piece is I have two, right? There is a variation, there are two variations in there. So the first one is d by dt prime delta R dotted with L partial derivative of L with respect to V. But there are two pieces, B1 plus B2. And the second piece is negative, as nicely pointed out by you guys. This is V dotted with V. Right. And finally, the C piece here plus delta T times dL by dt prime. Subtract out T1, T2. With me?
Wait, what did you, Taylor, say?
I'm Taylor expanding this whole function. Right, this is one variable. That's the second variable, and then that's the third variable. Right, I wrote down here there is an x, y, and z. This is the expansion in x that contributes to this. The change and the derivative. This is the change delta R and the derivative with respect to that variable. Here the change is this quantity with respect to the variable v. So that's here two changes and derivatives with respect to the variables v. And the third is delta t, that's a change, and the derivative with respect to that particular variable. Okay.
Okay, yeah,
At this point, we just have to expand it, and just remember that we are keeping only the leading order. I have already dropped a lot of higher order, so there is no point in keeping it here. Whenever I multiply this with any higher order, it goes away. So this is already delta t. So this with this goes away, this with this goes away. Or there are how many? 1, 2, 3, 4, 5 terms. This with 4 of them goes to 0 because it's higher order. But this one has to go with everyone. Right? This is 1, so it goes with everyone in there. So let me do that. So this is equal to this T1. This is T1 to T2. I'm currently expanding this 1 plus delta T into the Lagrangian. We can do one simple, it's not a simplification as such. We can at least recognize that what is this equal to in the, this is canonical momentum, right? So it just simplifies a little, at least ink. This is P, right? So you don't have to write so much, so it's here. P, this is your generalized force, but we have not used any variable for that, so we can just keep it like that. So that's here. So When I expand this out, one multiplies everything because it's leading order and everything, so this is L. Plus delta R. Dotted with R plus d by dt prime. R dotted with P. And multiplying still, so this is minus of d by dt prime delta t. Multiplying with V dotted with P. You remember V dotted with P shows up in the conversion of the Hamiltonian, right? Lagrange into Hamiltonian has that piece in there. And did I get, where am I? Finished.
Last one, delta t.
So, right, so it's plus delta t e l dt prime. That's one multiplying everything. Next, I have to do multiplication with this.
It's become 0.
Everything goes to zero except the first one. Right? So only one term is there. So that's d by dt prime delta t and just L. And the final piece now I can pull in, that's minus L. Bit tedious, but very soon we will see some pattern here. There are three variations, but still a little bit work needed. First is whenever this variation happens, that's the idea of calculus, right? The first should go away, so this always goes away, so that goes away, right? Otherwise, the variation that does not have a real meaning in a sense. It always, that's a generic. And next, we have made variations with delta R, right? That's the main idea, so delta R. But in certain places, it is showing up inside a derivative. Whenever it is inside a derivative, I want to bring it out, right? So this is inside, that is inside. And whenever I have something inside, I bring it out by using partial derivatives, right? And it gives you contributions at the surface. It is like saying d by dx, right? If you have f times g, this is like integration by parts. The idea of integration by parts is that you do d by dx of f of g. So this operator, this is a total derivative now, but that's not correct. So minus of f times dg by dx. If it was a single variable quantity, here, of course, we have to worry about implicit and explicit, but that's reasonably straightforward. It's all total derivative. So whenever I want to release this delta t, I do this, right? That's a trick I do. So do that in 3 of the terms, 1, 2, and 3 of the terms. I want to do that. And since I don't want to repeat steps, I'm going to do the organization also simultaneously. So this is T1 to T2 dt prime and d by dt prime and plus T1 to T2 dt prime, and I want to write everything with delta R in it. So that's how I'm going to operate. So first term is this, right? I'm going to organize them this way. So delta R will come in here. So that's this term, right? So I'm going to open a bracket. So L by R. Right, so that term has been taken care of. So that goes in here. The second term here, I have to use this trick. That is a total derivative, which goes in here. This is this, but that's not correct, right? This derivative should be acting only on this. So I have to subtract that out. When I subtract that out, so now delta R is released. That's this term with a minus sign. of dp by dt. And it is T prime, derivative of T prime. Okay, so these two terms are nothing but this quantity. Is that clear what I'm doing? I'm doing multiple steps at the same time. Hopefully it is not confusing.
So, yeah. Once you've taken dx f of g. Fine.
So this term here, for example, right, this is equal to d by dt prime of delta r dotted with b, right, using this idea. And I'll subtract that out, subtract the remaining out, so that's delta r dotted with d by dt prime of p. But I want to organize them in two lines. This piece I write here because I've taken a d by dt common out, prepared it that way. And the second term is delta r, that's delta r common outside, and d by dt prime of p. So that's this term. So I've taken care of two terms. The third term is very similar. Third term, again, I want to release this dt prime. Whenever I release this will hit the whole quantity. And d by dt is here, so that's minus of delta t. And let me open a bracket here, see what things are going to come up. V dotted with p. And when it hits on the other side, v and p, so that is a delta t now. It becomes plus delta t and d by dt prime of v dotted with p. Then open a bracket. That was this piece. Okay. This term here is isolated delta t, so that should go in here. I've kept things in this form, so maybe maybe put it somewhere here, right? So need some space more here. So that's plus delta L delta T prime. Okay. That's this bracket is going to close. Something more coming in. So that's this piece. Finally, this goes two places, d by dt prime total. So that's your L, but I have already a minus there, so that's minus L. And now you see why I organized them properly. You can recognize certain things. What is the quantity in the bracket here? That's a Hamiltonian, very good, right? So that's why I wrote it like that. And here again, you see v dot p, expectation is that Hamiltonian should show up. And this term, when I put it on the other side, it is the L by dt. I've already put the d by dt out, so that's minus L again. So and I can close this square bracket also. I think I can squeeze in a line there. So this is the main result, but we'll squeeze it in. So this is equal to, copy this again, T1 to T2 dt prime d by dt prime, and that's P delta R. It gives you a connection, right? So that's P, and this is Hamiltonian, right? So this is minus delta t Hamiltonian. It starts giving you a connection that momentum somehow has something to do with position. And energy or Hamiltonian has something to do with time. Like they have an association with each other. Remember quantum mechanics? You write Heisenberg uncertainty relation is between momentum and position or energy and time, right? So that's a connection showing up here. And these other pieces, let's write this as plus 1 to T2 dt prime delta R dot with. That's your equations of motion if you want. L by dr minus dp. That's Newton's equation. That's Newton's second law. Sorry. If I were set this to 0, I get Newton's second law there. And finally, I have plus delta t. And that's Hamiltonian. Total time derivative of the Hamiltonian plus the partial time derivative of the Lagrangian. And that's all variations. Until now, whenever we were doing functional derivatives, we were getting only this term. Now we have two more terms. Here, this is total, this is the variation in everything. The whole action is being weighed. Okay, so let's analyze this a bit. So here's a good news for you guys. That's 10 minutes. I'm going to postpone the homework, latest one, not the earlier one, to homework 8, right? Homework 8, that is of conservation principles. It was due on Tuesday. I'll make it due on the day of the exam. Okay. But you should be able to do everything now itself. We will have everything today, but I would like to talk more about that. That's it. I think last class we did a good bit of review, so that was the okay. So the variation and the action, you do all the position and time. Maybe I should let's give to point that out, right? What are the variations we are making? It is plus E2 so total variation, and that we are seeing there are two primary, or let's say three pieces that we see. Whenever you have something like this, this is a total derivative, right? This survives only on the boundary, right? This survives only at the boundary because these two cancel out and it's a total derivative. Is that clear what I mean to say? So if I have an integral dt d by dt of g of t, and let's say g is equal to sine of t. What is this answer? Very good, very good. So this is the same as very good. Right. So these two cancel out. This is a dg total time. So this is a variable itself. It is like dx, right? Integral of dx is equal to x, right? evaluated at 2 points. So these two goes away, d of g, so it is g evaluated at the 2 values, so it's t2 minus t1. So whatever I write next, it's a total derivative, it gets values only from the initial and final points. It is equivalent to the idea of conservative force, where it is path independent, correct? It gets only values from the initial and final point. I'm going to explicitly write that, but we will identify that as G in a minute. So this is dr dotted with P minus the Hamiltonian H. So that's a surface term. Earlier, we used to say that things goes to 0 on the surface. On the boundary, things goes to 0. That's this term. This is on the boundary. We always set on the boundary things to be 0, right? We say variation at the boundary 0, variation at the boundary 0. This doesn't show up earlier, but now it is showing up because we are keeping those variations at the boundary. What are the other things that we see? This is T1 to T2, T prime, and that is a variation with dr. And that's a variation at variation with respect to the function or the generalized coordinate. And finally, there is also the variation with time you can think of, which earlier we were not seeing. This is delta t. And that gives you the connection between the Hamiltonian and the inertia. Okay, so that's your 3 pieces.
That's what's expanding from what you're already seeing.
Yes, expanding in a sense, writing it as 3 terms instead of 2 terms, right? I had a square bracket, that's all. So that's a summary if you want, that's the result, right? Now we can analyze this, like the algebra led to. There's the only thing we have done is the variation in W, but now use the stationary action principle. Now we state the stationary action principle more carefully. Stationary action principle, if the boundary terms are 0, right, this is the stationary action, only it acts on this, right? Stationary action principle. With delta R at T1 equal to 0 and delta R at T2 equal to 0, right? This implies, is that clear? Like stationary action principle is when I set these two equal to be 0. In fact, set delta T1 and delta T2 also equal to 0. Delta T1 equal to 0, delta T2 is equal to 0. Then you have this equation coming in. So this is dP by dt is equal. That's Newton's laws. That's dP prime maybe. At this point, I don't know. Change the way. That's what we were doing all this time. Now I can still say that against this is stationary action principle. Stationary action principle, but now let's say delta R T1 is equal to 0, delta R T2 is equal to 0. And let me also say that the whole variation in delta R is 0. I vary only in time. So only in time, and delta R is equal to 0. Here, maybe instead of saying delta T1, I can say delta T is equal to, so the variation in T is equal to 0, right? That's your three quantities. If this was equal to 0, then that's also a stationary action principle. And then you say that partial derivative or the total time derivative of the Hamiltonian is equal to minus just for our purposes, this is good to have an idea of what this is. This means that if the Hamiltonian was independent of the time, then you can identify it as energy. Only if the Hamiltonian is independent of time, you can identify it as energy. That's the physical part of that, but otherwise it just says that time derivative is this, which is a true statement. This is a true statement, exactly like this, Newton. We have used this, we have seen this before and earlier in your homework. The first question in your homework is to show this more explicitly at a very simple level, using chain rule of partial derivatives. You can show that this is true using the definition of Hamiltonian and Lagrange. So that's two of this, and now comes the real crux of the statement that if you use these two equations, like apply stationary action principle, use your equations of motion. These are equations of motion. That means these two terms are gone, right? That means the system is really in action in the sense that this is the trajectory of the particle. This decides the trajectory of the particle. For the trajectory of the particle, which is how a particle behaves, the action changes in the following form. So when the particle is moving, what is happening to the action? This is how the action changes as the particle is moving. This is equal to T1, T2, dt prime, d by dt prime, and let me write this as G of T prime. I think I can stop writing T prime and just write T, right? It's a dummy variable. G of T, where G of T is called the generator, is, you can say generator of dynamics if you want. It is actually, that is what generates motion, one and minus of delta T times H. The minus sign is coming up very naturally. That is the signature of the Lorentz invariance, special relativity, the time and position are showing up there. And you can also say this is equal to G of T2 minus G of T1. This is called the generator. And the idea would be, if I give you some variations, let's say translation, what happens to the action? If I do a translation in time, what happens? If I make rotations, what happens? And that is what you see in your homework. In the homework, the first problem or the second problem is about translation in space, translation in time, rotation in space, rotation, there is no rotation in time, and boost variables. The main idea we are going to say is that if the action does not change under rotations, what will stay the same for the system? Can you imagine?
The action doesn't
Change for rotations. Let us say there is a system, Earth going around the sun, and I have a coordinate system. If I rotate my coordinate system and still all the physics remains the same. Suppose we have that scenario. We don't have that scenario. For example, now I'm looking at you guys. That's my coordinate system. My eyes have a coordinate system. If I rotate, my world is different, right? I see you guys on my right. So things have changed. If that happens, if the system is different, that means angular momentum is not conserved. If I can rotate around and I see the same world around me, that means angular momentum is conserved. Right? Most of the time, if you remove all the planets around us in a distant world, when we see our universe, it is very symmetric. Everywhere it is the same things we see. Mostly homogeneous, even though at a very close zoomed in way, you see some star here, some star there. But to a certain scale, there is a lot of uniformity in them. Then you say that, okay, everything looks the same. That means angular momentums must be conserved for that. So rotation has connection with angular momentum. Next, you say, I'm standing here. I move to my left. So that's translation along a line. And then again, ask, has the world changed, right? Things are different. If I move this way, I'm closer to Pradeep, right? And if I move a little that side, so I'm translationally moving that side, I'm closer to Dilakshri, right? So these are different worlds for me. There's a clear distinction. But you can always think of a system where you do this movement and you don't see any change. If you don't see any change, that means linear momentum is conserved. Okay, so translation in time, translation in space is linear momentum. Rotation in space is angular momentum. Translation in time. So I sit here and let us say I'm sleeping. The same story, you can say that while I'm sleeping, you displace everything, like you displace my bed, right? Will I notice any difference or not? If I do not notice any difference in time, for example, I put myself from today to tomorrow, like I jump to future, let's say, if that was in an abstract sense possible. And is there any difference? Can I make any sense out of it? If I don't make any observation, that means energy is conserved. If translation in time doesn't have any effect on me, then energy is conserved. Translation in space is linear momentum. Rotation in space is angular momentum. And finally, the classic one, which we always say, is relativity. If you say velocity, if I move two cars moving with respect to each other, uniform velocity, that's a boost, right? The special relativity of Einstein, that should also have a operator associated with that. That usually you don't see in undergraduate physics at all. It will be called the boost operator. You don't see that earlier, and that has connections with spin of a particle. So these, there are 10 operators here. One energy, that's scalar. 3 components of linear momentum, right? That makes it 4, right? 3 components of angular momentum, that makes it 7. And 3 components of the boost operator, that makes it 10. These are the 10 components of Poincare algebra, you can say. These are the 10 classic operators that you will talk about, conservation principle. And we will do that next time. We will be able to get all of, in your homework, you see that. Except for the boost, you see that in your homework. Okay.
Yeah, so.
Yes.
With variation of boundaries. But at the end, we make the variation zero.
No, my point was that here, now I have everything. And now I have to get back my old equation. If I do this,
Then
I get back my old
Oh,
equation, right? This was my, whatever we did. But now we say that suppose I use that equation. So this is equation of motion is used, then I get this,
oh,
right? This is the new part. The change in the action for an actual particle. Like before you set this, it is not an actual particle. Like it could be any particle. The actual particle picks this term. When you set this to 0, that's an actual trajectory, right? For an actual trajectory, this is valid. So this is the statement. For an actual trajectory where the dynamics is going on, when the ball is being dropped, when it is falling, this is valid. So physics has something to do with this, and that's what we will. Or we will, at least done most of it, we will talk about it. Thank you.